Dear students, in the last class we discussed about Theorem's theorem. In today's class we are going to discuss about Norton's theorem. Assume that the network enclosed below is composed of independent sources and resistors. Imagine that the network has more number of resistors and more number of independent sources. So we have to reduce the circuit by using Norton's theorem. So Norton's theorem states that this network can be replaced by a current source shunted by a resistance R. That is, the complex network is replaced by a simple current source, that is short circuit current source, in parallel with the Norton resistance that is equivalent to Thevenin resistance. So it is a statement of Norton's theorem. It states that the current source is a short circuit current of the network, that is the current obtained by sorting the output of the network. We have to short circuit the load resistance and find out the value of short circuit current. That short circuit current is the Norton current, that is a short circuit current ISS. The resistance is the resistance seen looking into the network with all sources deactivated. With all sources deactivated, we have to look back the resistance. That resistance is known as RTH, that is equivalent to Norton resistance. So ISS is the short circuit load current and RN is the open circuit, that is the deactivated source with looking back resistance is RN. So ISS in parallel with RN gives the Norton's equivalent circuit. So we recall the following from source transformation. The Thevenin equivalent circuit can be replaced by a Norton equivalent circuit. That is, if the voltage source is in series with the resistance, can be replaced by current source in parallel with the resistance. Voltage source in series with the resistance is replaced by a current source in parallel with the resistance. The value of current is equal to, according to Ohm's law, V by R. So in view of the above, if we have the Thevenin's equivalent circuit of the network, we can obtain the Norton equivalent circuit by using source transformation. But we are not finding this method. However, this is not how we normally go about finding Norton equivalent circuit. We can see one example. This is the example. Find the Norton equivalent circuit to the left of terminal AB for the network shown below. Connect the Norton equivalent circuit to the load and find the current in the 50 ohm resistor. So you have to find out the value of current flowing to the 50 ohm resistor using Norton's theorem. So we have to short circuit the 50 ohm, remove the 50 ohm and short circuit the 50 ohm by using a wire. Then find out the value of that short circuit current IS flowing through AB. That is the ISS, that is Norton current, short circuit current. So it can be shown by standard circuit analysis, that is by loop analysis. We have to find out the value of short circuit current ISS, that is equal to 10.7 ampere. By solving the network, we can find out the value of short circuit current by using loop analysis, that is ISS equal to 10.7 ampere. So it can also be shown that by deactivating the sources, so that is we can remove the voltage source and short circuit the current source. Remove the voltage source, that is open circuit the voltage source and short circuit the current source and find out the looking back resistance. That resistance is known as Norton resistance, that is also called as Thevenin resistance. So the Norton resistance equal to 55 ohm from the back of the AB. Then Rn and Rth will always be the same value for a given circuit. The Norton equivalent circuit tied to the load is shown below. Therefore, the 10.7 ampere is the short circuit current and 55 ohm is the Rn, that is equal to Rth. That is in parallel with the current source 10.7 ampere. That is in parallel with the 50 ohm. Now the 50 ohm is replaced in AB. Now we can find out the value of current flowing through a 50 ohm resistance by current division rule, that is opposite resistance by total resistance into total current. So we can find out the value of current flowing through the 50 ohm resistance. Next example. The example illustrates how one might use Norton's theorem in electronics. The following circuit comes close to representing the model of a transistor. For the circuit shown below, find the Norton equivalent circuit to the left of terminal AB. It is the equivalent circuit of transistor. So first we have to find out the value of Norton resistance, that is equal to VOS by ISS. VOS is Vx, that is equal to minus 25 into IS into 40. Minus 25 into IS into 40. That is the in parallel the voltage is same. Therefore by using Ohm's law, V equal to I into R. Therefore I is 25 into IS, R is 40 ohm. Therefore the value of Vx is minus 1000 into IS. So VOS, open circuit voltage VOS is minus 1000 into IS. Then Rn is VOS by ISS So VOSS is minus 1000 into IS. ISS is already we know 25 minus 25 IS. It is in the downward direction. So the current will be in the negative value. So minus 25 into IS. Therefore the answer is 40 ohm. So Norton resistance is 40 ohm. Then from the mesh analysis, we have to find the value of IS. That is given by the minus 2.5 milliampere by using mesh analysis. Therefore, IS is equal to minus 25 into IS. ISS is 25 into IS value becomes to minus 2.5 milliampere. Substitute the value of IS. Therefore, ISS is 62.5 milliampere. Therefore, the equivalent circuit of Norton resistance is 40 ohm and IN is, that is the short circuit current is 62.5 milliampere. It gives the equivalent circuit for the transistor.